So first up, a definition followed by an understanding of what it means to have a neutral solution and when a pH of 7 is in fact not neutral, and finally how to calculate the pH of an alkali solution. And as always, pause the video and make sure you download your own copy of this PDF so you can be making your own revision notes. Okay, so let's get started. So what is the ionic product of water? So as water can dissociate, we can write this as a reversible reaction as it is in equilibria. So here we have our Kc expression, but because equilibria lies so heavily to the reactant side, we can assume that the concentration of water remains basically unchanged. So we can kind of rewrite the expression like this, and because Kc and the concentration of water remains unchanged, it is basically a constant. And because this is an important constant, it has a name, and that name is the ionic product of water, and here is its symbol. So here, so Kw equals the concentration of hydrogen multiplied by the concentration of the hydroxide ion. And yet it has been experimentally determined to be 1 × 10 to the negative 14 at 298 Kelvin. So here we go. So this is our constant value here, the ionic product of water. So this relation is fixed. So that means that the product of H plus and OH negative is always going to be this number here. So we can think of it like a seesaw. So if one goes up, then the other has to go down. So this is a really important relationship to remember, as we move through the topic. And starting with our last point for today's video. But before then, we need to look at what is a neutral solution. So for a solution to be neutral, the concentration of hydrogen ions and hydroxide ions has to be equal. So it has to be equal. And at 298 degrees Kelvin, at pH 7, this is true. So at pH 7, the hydrogen ions and hydroxide ions are equal. So at pH 7, we have a neutral solution. However, as we already know, it is an equilibrium. Equilibria constants, they change with temperature. So with this equilibria, the forward reaction is endothermic. So that means that when you increase the temperature, due to Le Chatelier's principle, the reaction wants to lower the temperature, so it progresses in the endothermic direction, which means that the concentration of the hydrogen ion and the hydroxide ion, they increase. So we can have a look at what's going on with the graph here. So as temperature is increasing, we can see that the value for Kw is also increasing. So the hotter it gets, the bigger Kw is. So this means that the pH of 7 won't necessarily mean you have a neutral solution. So this is only true at 298 degrees Kelvin. So let's have a little look at an example to see what's going on. So at 60 degrees Celsius, Kw has this value here. So it's a bit bigger than the usual Kw constant. And for it to be a neutral solution, these two need to equal each other. So we've got our expression here from before, but this number has now changed. So this has changed, but these need to be equal for it to be neutral. So we can rearrange the equation. So basically, these need to be the same value. So this means if you just root this number here, we can then find out the new hydrogen ion concentration when we have a neutral solution, and that is this number here. Then putting our hydrogen ion concentration into our pH calculation, then we get this pH here. So this time, in this case, at 6.5 is our neutral solution, so it's not 7. So it's not slightly acidic, it is neutral because these two are equal. So this doesn't come up that often, it's just something to be aware of, as you could get a question about it in the future. Okay. So let's look at our final thing, how to calculate the pH of an alkali solution. So here's our question. So what is the pH of a 0.05 moles per decimeter solution of potassium hydroxide? Well, potassium hydroxide is a strong alkali, which means it fully dissociates. So whatever the concentration of the solution, that's going to be the concentration of our hydroxide ion. And yeah, this is the relationship that we need to use. So this relationship is very, very important because yeah, if we know the concentration of the hydroxide ion, we know that this is a constant, so then we can solve for the hydrogen ion concentration. So we know that this is 1 times 10 to the negative 14. We know from the question that this is 0.05. Solve for H+, so we've got our number there, and then yeah, we are using the pH calculation to figure out the pH, and here we go. Here is our answer, and yeah, to 2 decimal places, because our question is to 2 decimal places. So there we go. So this is a taster of what's coming up in the future, as yeah, this relationship comes up a lot. Finding out the pH comes up a lot, so yeah, I hope that all makes sense. Okay, so yeah, thank you for watching, and as always, please do like and subscribe. It will mean so much to me, and yeah, I will catch you in the next one. Ciao.